Hi everyone, my name is Ram and I'm a PhD candidate at the University of Michigan and lead researcher at SensorPlan. In this joint work with researchers from EPFL, Cloudflare, and the University of Maryland, we explore ways to passively detect global connection tampering. So, what do we mean by connection tampering? We are referring to the restriction of application layer TCP traffic between a client and a server by a middle box that is performing deep packet inspection in the network. These middle boxes, now extensively deployed by organizations and even governments, restrict access to certain content on the network, usually either by dropping packets or by closing a connection forcefully using a TCP reset. Obtaining a global understanding of this type of connection tampering not only allows us to track restrictions to freedom on the internet, but also helps service providers understand and explain reasons for unavailability. A lot of work in the past has gone into studying tampering, especially using active measurements. For years, we've built up measurement platforms like Uni and SensorPlanet, where we collect vantage points and volunteers in many regions, create block lists of internet content to test, and run active network measurements to see what is blocked. But active measurements are not driven by real world user data, and thus they may miss parts of the picture, such as what users are trying to access at which time. Even with the large amount of work we've put into procuring vantage points, it is still hard to obtain data over time from every network. Also, from years of working on SensorPlanet, I can tell you that test lists are incredibly hard to curate and maintain. And even then, they may not reflect what users are interested in accessing currently. But where there are challenges, there are also possibilities. So far, the focus has been on the client's view of connection tampering. But the client is not the only participant in the connection, right? Maybe there's ways to look at connection tampering from the point of view of a server too. We use the insight that tampering signals are not only visible to clients, but also to servers. It works to our favor that the tampering behavior of middle boxes, especially those deployed in censorship systems studied in previous work, represent sequences of packets that client applications typically would not send. Using this insight, we developed a method to detect connection tampering from completely passive data collected by the server side. Our detection system locks packets on a server as they arrive, looking for when tampering happens using a set of specific signatures. When tampering is detected, the system analyzes preceding packets in the TCP connection to identify the triggers that cause tampering. Now, imagine all of the things that such a detection system could see if deployed, say, at a large cloud provider. Well, that's exactly what we did in deploying our technique at Cloudflare, a large CDN provider that serves about 17 to 20% of popular internet content. Our system is deployed to observe a 0.01 sample of all inbound TCP connections at all of Cloudflare's points of presence. The system is running live at Cloudflare's Edge network right now, but for this talk, I'll mostly zoom into a 2-week period where we observe traffic from 247 countries. So, how does our technique work? When we realized tampering middle boxes send traffic that looked abnormal, we looked through the data that Cloudflare receives and combined that with insights from previous work in censorship detection to come up with a set of 19 tampering signatures, which are packet sequences that are indicative of connection tampering. First, our post-SYN signatures detect tampering during the TCP handshake before any content has been exchanged. So these signatures mainly identify IP-based blocking by middle boxes. The post-ACK signatures detect tampering that occurs during the transfer of the first data packet after the handshake. For instance, these signatures detect the INPAT censorship system in Iran that drops the first data packet containing the TLS client hello. In our post-push signatures, the server receives the first data packet, but immediately also receives a tampering signal, such as a TCP reset. This is exactly what we've seen, for instance, in previous works about the Great Firewall. The advantage here is that we as the server can see the exact trigger that caused the tampering. Finally, we also develop signatures that capture tampering that occurs further into a TCP connection, usually performed by enterprise firewalls with visibility into encrypted traffic. Now, the key question here is, do these signatures actually show tampering by a middle box? Or is it the effect of some applications from clients? To make this distinction, we look at certain information in the TCP headers, such as the IP identification field. We observe that most clients follow RFC recommendations and increment IP ID values in the same connection by 1. So, in the absence of tampering, we'd expect no big IP ID change between consecutive packets. But flows matching our tampering signatures show an abnormally high IP ID change between the reset packet and preceding packets in the connection. So this indicates that they may be generated by a different TCP stack belonging to a middle box. Similarly, the change in the time to live field was also 0 for packets in non-tampering flows and much higher for packets in tampering flows. Okay, so now to some findings from our global analysis of passive measurement data. In this graph, we have a few select countries on the x-axis, and the y-axis shows the percentage of flows matching each signature. The distribution of each of the signatures vary across countries. Some signatures are predominantly seen only from certain countries, and this again indicates that we are detecting specific tampering behavior. Globally, we see that around 20% of all connections received by Cloudflare, a really large number, match our tampering signatures. So our passive measurements give us a great idea of the magnitude of real-world tampering, something that's not possible in active measurement contexts. We see that more than 80% of connections that we get from Turkmenistan match our tampering signatures. But such high levels of tampering are expected since Cloudflare and other CDNs are largely blocked in Turkmenistan. We also see significant levels of tampering in Peru and Uzbekistan, 2 countries where tampering has not been studied in detail by active measurements previously. And this shows that passive techniques can remove the need to find vantage points in new regions. Finally, we were also able to confirm previous observations about the behavior of censorship systems in China and Iran. And we studied their behavior towards tampered content at large scale. Because our study looks at real-world user data, we are able to see user access patterns and obtain observations at granularities that previous studies, active measurement studies, have not been able to do. For instance, we look at tampering of user requests across time, and we find that tampering rates follow a diurnal pattern in many regions. We're also able to get real-world data about blocking during times of censorship events. So, for example, following protests and increased censorship in Iran last September, more than 30 to 40% of the country's traffic was affected by tampering. When we were able to see the client's requests, we took these requests and we categorized the domains to identify user access patterns. That is, what categories of domains are highly blocked in the country. For instance, we see that traffic to adult websites make up to 13% of tampered traffic globally and 18% of the tampered traffic in China. But in fact, we are able to learn even more. Even though adult websites only make up 18% of the tampering in China, we see that more than 50% of websites within the adult themes category itself are tampered. And this gives us a great idea about the completeness of the tampering of adult websites in China. One of the things I really think passive measurements can do for platforms like SensorPlanet is help us create better active measurement test lists by augmenting information about what content users in the country are actively trying to access. So far today, I've talked about what passive measurements can bring to the table and how such analysis can help us in the internet freedom community study restrictions to online freedom globally. But we're only getting started, and we need more. Our signatures can be applied to any passive measurement dataset, and we especially see benefit in other large service providers and ISPs adopting our techniques and contributing to the community's knowledge about tampering. We encourage ISP operators and service providers to contribute data and help bring transparency to internet restrictions. To summarize, we performed the first global and completely passive study of connection tampering driven by real-world user data and the set of tampering signatures that we've developed. Thanks to the extensive and dedicated efforts of the people in this paper, teams at Cloudflare, especially the Cloudflare research and radar teams, our techniques are now deployed at Cloudflare. And right now you can go to Cloudflare Radar and check out live real-world data that we are collecting about connection tampering. Thank you so much for listening.